Hello, I feel really honoured to be invited to give this keynote, and I apologise that I'm not able to be there in person. This is a wonderfully exciting time to be working in the semiconductor and computing industries, where these technologies are becoming central to our societies and have been created enormous capabilities and opportunities for all of us. Indeed, the demand for ever more computing seems to be insatiable, particularly with the rising use of AI. Meeting this demand is not easy, but the history of the semiconductor industry is that it is continually innovating new technologies to meet the expectations that are put upon it. One of these key developments emerging at the moment is the transition from monolithic SoCs to packaged chips that are made up of multiple different chiplets. This move, which has been talked about for many years, is now very firmly a reality. It allows for greater scaling of the system and can help address things like yield issues that come from very large monolithic silicon. It also enables the mixing of different technologies and process nodes in a way that gives the best of all worlds in terms of the process technology choices. For example, we can combine an advanced logic subsystem built out of a leading-edge 2 nanometer or smaller geometry with a mixed signal design of a larger geometry better suited for analog processing. Indeed, as geometries for advanced logic continue to shrink, so we may need to use this process heterogeneity that comes from chiplets to create optimal combinations of memory and logic at a surprisingly fine grain. The advent of AI has increased both the amount and the diversity of computing needed by the different computing solutions, such as those used in high-performance compute, advanced communication protocols such as 5 and 6G, in personal client devices such as PCs and smartphones, and in software-defined vehicles. In each case, the amount of compute required is growing rapidly as people increasingly use AI in a wide variety of different computing needs in different ways. This need for diversity comes at a time when a leading-edge SoC has become very much more expensive to create, driven by the increased complexity of the system design and validation, and the manufacturing cost that comes from using these leading-edge nodes. This then means that each design will typically require a substantial volume of product to amortize the fixed costs of the tape-out to that manufacturing process. Chiplets provide a potential route to address these challenges by enabling a greater level of reuse of components of the system, paving the way for an increase of customization of market-specific SoCs without being overwhelmed by the cost of their development. Prior to the advent of chiplets, a system designer really had two choices when building a system to fit a particular market. They could use an off-the-shelf part and construct their solution at a board level, or they could invest in building a bespoke SoC using a range of IP from a variety of vendors, including, of course, ARM. The success of the ARM ecosystem has shown that many companies can effectively build customized monolithic compute solutions for particular markets, and we believe that this will continue to be used for many solutions. But chiplets provide a further way to enable the creation of custom solutions that avoids the work and cost of having to create a full monolithic design. Essentially, the base compute subsystem can be built as a standard chiplet using ARM IP, which, having been designed once, can be reused in many systems going forward. This standard compute chiplet can be combined with a custom chiplet or multiple chiplets that contain valuable differentiating functionality, such as a particular AI accelerator or something else that is targeted for that target custom solution. Over time, we see the chiplet trend evolving to really an emerging ecosystem of interoperable and reusable chiplets provided by multiple vendors. Now, this is a vision that's relatively easy to describe, but actually will take a lot of standardization and industry collaboration to make real, and I suspect will take a reasonable amount of time to fully emerge. ARM has been working on a range of standards to help with the move to using chiplets. One of the important challenges is to work out how to partition up much of the system-level functionality, such as the power control, the interrupt management, and security features across the different chiplets in a way that enables reuse and gets the best results out of the system. To address this, ARM has worked with many silicon vendors and system designers to develop the Chiplet System Architecture, or CSA. ARM has made the first public beta release of the CSA earlier this year, and we are inviting companies to work with us to further this standardization effort. The specification is available from ARM's developer website, which you can get to by following the link on this QR code. In October last year, a collaboration was announced between ARM, Samsung Foundry, ADT Technology of Korea, and Rebellions, an AI chipmaker, to develop a large-scale AI platform using chiplet technology that we brought to market by Rebellions. This very complex, high-performance computing platform contains 2 compute chiplets, each comprising a compute subsystem from ARM with 64 Neoverse v3 cores. These chiplets are being built by AD Technology on the Samsung 2nm process and connect to 4 Rebel H NPU chiplets that are being built by Rebellions, which provide the AI acceleration and which in turn connect to a set of Samsung HPMs to provide the memory bandwidth required for the AI training and inference. The complete solution, integrated in SoC, is expected to give around 2 to 3 times the efficiency performance over the current solutions. This sort of multi-party collaboration is enabled by key standards such as the CSA to guide system architecture, AMBER-CHI for the interconnect protocols, and UCIe for the physical layer of the chip-to-chip interfacing and communication. These standard chiplet systems are really impressive and are allowing an almost unimaginable level of computing functionality to be delivered in a single package. But I come back to a statement I've been made on many occasions over the 20+ years that I've been leading the ARM architecture. Security is the greatest challenge computing needs to address to meet its full potential. As computing becomes more and more central to our lives, so the limits of what we are prepared to use computers for will be set by the degree to which we can trust these systems. At the same time, the ubiquity of computing solutions makes them an ever more attractive target to criminals, whose sophistication is undoubtedly increasing. And the geopolitically uncertain age in which we live also means that the concerns of computer security and national security are becoming intertwined, and so add to the pressure to improve the security of our computing systems, including against very well-resourced attacks, potentially even from state actors. One of the problems with computer security is that there are a great many threats and avenues for attack, and the computing system needs to be made resilient against all of them if it is to be properly secure. As a result, over the years, ARM has added a great number of features to address various security issues. We've added features such as memory tagging to address the persistent issues of dynamic and static memory unsafety, pointer authentication, branch target indicators, and guarded control stacks to protect against various forms of code reuse attacks, and key partitioning technologies to enable confidential computing, starting with Trust Zone in the early 2000s and now extending to our realm management extensions as a key part of ARM v9 and as the foundation of the ARM confidential compute architecture. A little over a decade ago, when we started off working on the realm management extensions in ARM, the primary consideration was ensuring that the data that is being used within an application or virtual machine is protected from observation or undetected modification from the higher levels of software such as the operating system or hypervisor. And this is still a very important part of the threat model for confidential computing. But the emergence of AI as a key workload of our times increases the need for confidential computing in 2 ways. One is simply that more user data is being used within the same application as part of the AI processing, and that needs to be protected. But in addition, particularly for closed source models, the code and the data values of the application itself are also critically important to protect. Companies working in the field of AI tell us that it is vitally important to protect the architecture and details of the AI model, as well as protecting the trained weights of that model. These models are very valuable pieces of IP, given the extraordinarily large amount of computing and energy that they take to generate. And so they need to be protected from either reverse engineering or being subverted. Indeed, recent US government export control regulation has explicitly called out the need to control the exporting of AI model weights that have been trained with very large levels of compute, which is a clear recognition of the importance of the security of these systems. This increases the need for confidential computing even further, and in ARM's view would expand the demand for such technology beyond the traditional usage areas such as cloud computing with its multi-tenanted servers to more closed environments such as the client systems of a PC or mobile device, or also in the automotive space. The principle of ARM's confidential computing architecture is to allow a virtual machine to be moved from the normal compute environment that it is running under a standard hypervisor to instead run in a realm where the virtual machine's execution and data cannot be seen by the hypervisor. However, the hypervisor remains in control of the resources that are used by that virtual machine. The contents of the realm are protected from the normal world and from other realms by both hardware protection schemes and by memory encryption, with the contents of each realm being given its own set of encryption keys as part of our memory encryption context feature. A key part of the confidential compute functionality is that the software that is running in the realm is able to use attestation to ensure that it is genuinely running in a realm on hardware that it can trust, and that the layers of the root and realm management software are also trustworthy. This is important as it allows software to know that it is in an execution environment which it is safe to install high-value assets such as the AI model and its associated weights. The ARM confidential compute architecture has a number of key features that make it particularly well suited for these new AI workloads. ARM-based realms offer defense in depth, as separate instances can be created inside the same realm. This allows runtime services to move from the hypervisor to the realm while being partitioned from the protected application and its data. This capability also means that applications can be moved into a realm without any modification, so simplifying the use of realms. The hypervisor can allocate as much of the system memory as it needs to a realm. There are no artificial constraints imposed by the architecture, and we all know that AI models typically require a tremendously large amount of system memory. And very importantly for AI, the RME device assignment capability allows accelerators to be assigned into a realm to be used securely by the realm VM. The ARM confidential compute architecture uses PCIe's TD-ISP and IDE security features to provide the security with PCIe accelerators, covering both device management and securing the link between the accelerators and the CPU. ARM's confidential compute architecture is associated with three main execution states: the normal world for running the non-confidential compute workloads, including the host hypervisors such as KVM, the secure world for running first-party secure software as part of our trust zone architecture, and the realm world that is used to support realm-based confidential computing of third-party workloads. The switching between the normal, realm and secure worlds is performed by the TFA monitor operating in a fourth execution state, the root world. The realm management monitor is the controlling software of the realm world that interacts to requests from the hypervisor in the normal world to allow the management of the realm VM execution. The RMM communicates through the TFA monitor in the root world to control the memory transitions that occur between the normal physical address space and the realm physical address space. The RMM is responsible for managing communication and context switching, but it doesn't make policy decisions, such as which realm to run or which memory is actually going to be allocated to a realm. Those decisions remain with the host hypervisor, consistent with the host hypervisor's role in managing the resources of the overall system. ARM has released open source software for the realm management monitor that runs at realm EL2 and the TFA monitor that runs at the root of trust of the CPU. This software is available from trustedfirmware.org. To close off my presentation, I want to give a brief introduction to Fujitsu's Monaca SoC, which brings together the two themes from my talk. Fujitsu Monaca is a custom 3D chiplet-based SoC being developed by Fujitsu using the ARM v9a architecture with the realm management extension and ARM's confidential compute architecture. This SoC will form a confidential compute AI solution for use in data centers and is taking the open source firmware and software ecosystem available from trustedfirmware.org. This is a great example how the various technologies I've talked about in this presentation come together to ensure the confidentiality of this custom silicon. There is a dedicated presentation on Manaka being given by Darshan Patel and Tatsuya Kitamura of Fujitsu in a separate session in this conference, so I will leave it to them to talk about more information about their design. In addition, given the importance of attestation to the overall confidential compute story, there is also a talk at this event on Attestation Everywhere by Paul Howard of ARM and Kevin Zhao of Linaro. For people who want more information on the main themes of this talk, there are QR code links provided here for 3 of the key technologies from ARM. That is the chiplet system architecture, ARM's confidential compute architecture, and an introduction to our compute architecture, attestation, and Verizon technologies. Overall, I hope all these talks and architectures show that ARM has a lot of technology that is invaluable to ensure the confidentiality of custom silicon. Thank you.